We've already said that Raspberry Pi 5 is the longest duration program that we've ever run at Raspberry Pi, and it stretches all the way back to 2015, right? It stretches all the way back to kind of Raspberry Pi 2, the era just after we launched Raspberry Pi 2. And probably the first thing that we started working on this platform is RP1, the I/O controller. Well, so what is RP1? What does it do?
So RP1 takes all of the traditional Raspberry Pi peripherals, the GPIO, the MIPI interfaces, USB, Ethernet, what else?
Analog television?
Yeah, analog television.
Analog audio somehow?
Yes, analog audio as well. Yeah, SDIO.
Yeah. As well. And all of the low-speed, so you've got the GPIOs and all of the low-speed peris, the MUX options that sit behind that, the UARTs and the SPIs and stuff.
Yeah. I guess we don't have analog audio. We have PWM output that could do analog audio if you add the gubbins, but.
Sorry. So we take all of those peripherals and we've put them onto our own chip, and that allows us to keep that as a separate south bridge, and then we can migrate our main system on chip down to smaller geometry processors.
Starting at 16, so 16 nanometers is the first instantiation of this. But in principle, you could then take basically that same digital design, the 2712 digital design, and you could move that down to progressively smaller nodes without having to re-procure all of the analog in the system, right? And so this is all of the I/O. This is the Raspberry Pi-ness of a Raspberry Pi, right? Packed into a single piece of silicon and now remote. So how does that then talk to the main SoC? How does that talk to 2712?
So that's over a PCI Express link. So all of the masters on RP1 can talk directly into the system memory on the main SoC, and similarly the peripherals in the RP1 address space are mapped into the main SoC as well. Right.
So from software's point of view, these things might as well be integrated. I mean, it's a nice thing about PCI Express, right? Yeah. Is from the software's perspective, these may as well be integrated onto the main piece of silicon. Yeah. Obviously, it's a somewhat higher latency link than if they were on the core silicon. Yeah. Okay, so and that's a four-lane Gen 2 interface, right? Which is 4 gigabits of payload per lane. 16 gigabits, 2 gigabytes a second. So we've got 2 gigabytes a second of read and write bandwidth between the two sides of the link. And then when you look on the board, I mean, it's pretty obvious. You can see this from space pretty much when you look at it on the board, right? It's this enormous motorway of lanes with their capacitors, with their series capacitors in them that runs between the core SoC and RP1, which is in the top right-hand corner of the board.
Yeah. If you look at the board, the way up the silk screen is printed, which a lot of people tend to tell us is actually the wrong way up. There we are.
Yeah. So, well, I think people think it's the wrong way up because then you naturally think your HDMI connectors
comes out the back. Yes,
back,
no, I know.
Which is a reasonable. It's a historical artifact.
Yeah. One day we may fix even that.
Yes. We could have fixed it just by turning the silk screen around yesterday.
Sorry. Digression.
Yes. It provides all of this functionality. How's that all stitched together? So inside an RP1, inside what we internally call Project Y, how's that all stitched together? What links the various masters, the various bus masters? What links those to the PCI Express complex on the chip?
So we've got a AXI-based bus fabric, which I think is 128-bit data and more than 32 address, but probably 40-bit address, something like that. So the PCI address bus comes in as a master and then can talk to any of the slaves, and then similarly all of the masters on RP1 can talk out over PCI Express, which then lets them access the DRAM on the main SoC.
Right. So you've got a bunch of these components that you've got. We should talk about USB actually, because USB is interesting. That's somewhere where we've got a really interesting uplift in performance over. How did that work? How did that work sort of topologically on Raspberry Pi 4, and then how is that different and better on Raspberry Pi 4?
So on Raspberry Pi 4, we've got a single lane of Gen 2 PCI Express to this effectively a hub. So it's PCI Express to USB 3, and then it's hubbed out to two USB 2 ports and two.
So you've got 4 gigabits of upstream bandwidth.
That's right.
And then you've you've got a pair of, in the way we use it, you have a pair of threes. And
2 3s and 2 2s, but they're all effectively behind. They're all sharing that bandwidth. Whereas in Project.
So on Raspberry Pi 4, you can't even run one of those USB 3s at peak rate, right? You can't.
Not if you're, well, yes.
You've got 5 gigabits, you've got 5 gigabits of nominal payload, but you've only got 4 gigabits upstream. So you can't even run. Now, how's that different on Project Y and Pi 5?
So we've got 2 USB 3 controllers. I think each one has a USB 3 port and a USB 2 port. Yeah. But because of the bandwidth of the PCIe link, we should be able to run both USB 3 ports at full bandwidth.
Yeah. So if we'd gone for that hubbed architecture, we probably still would have been limited to 5 gigabits. We'd have gone from 4 to 5 in practice, because we've got 2 separate controllers and we've got lots of upstream bandwidth. We now genuinely get the 5 out of each of the ports separately. Which, of course, if you want to use this to build a RAID array or something, that's a much better solution, right?
Yeah.
It's also worth saying that we've had this controller in the lab for a long time, and we've done a lot of work on making sure that the software works and any bugs in the controller have been ironed out. So actually, there are fewer workarounds for this controller than any other silicon I think we've ever had on any Raspberry Pi, right? So it's the least quirky.
Jonathan spent an enormous amount of time looking, particularly at some of the corner cases you find with UAS. UAS devices, which are, they're fast and they're a little bit subtle in how they behave. We really are pretty confident we've squeezed all the bad stuff.
We've had a long time to sort of, massage it into doing things properly.
Yeah. We've had this design in the lab for 3-ish years roughly. When did B0 come back? It's another pandemic era thing, isn't it?
Yes. Was it 20? Gosh,
Jonathan in there in the lab in 2020.
It's all a bit of a blur. I think COVID's kind of like taken this 2-year window out of everything. But
well, it's this weird thing with Raspberry Pi 4 where it launched in 2019, so it's demonstrably now a 4-year-old product, and yet I somehow think the combination of the pandemic and then the supply chain challenges, I sort of somehow feel like Raspberry Pi 4 is a new product. It sort of feels like a product that's only really just getting into its stride now.
We launched RP2014 in 2021.
Yeah, it's incredible.
Right? I mean, actually, so it must have been 2020 when we had the stepping silicon.
Yeah. And so we've been able to look at the USB 3 behavior since then. We've had it in FPGA for slightly longer than that. The nice thing about having all of these designs in FPGA, we should talk a little bit about prototyping actually. Yeah. So having all these things in FPGA has meant that it gives you it's that godlike perspective that you get when you can put instrumentation onto any net. It might take you overnight to rebuild your FPGA image, but you really can get in there. And instrument everything.
It also allows us to get proof of concept Linux drivers for everything, and you can do all up bandwidth testing to the best of your ability anyway.
So we've got better USB. We have better. I mean, I think we have better MIPI now. We have slightly different MIPI, but we have better MIPI. So what does the MIPI subsystem look like on the platform? This is the camera and display.
Yes, yeah. So there's 2 MIPI PHYs, and each MIPI PHY, so the physical interface, can be either a camera or display.
So these are transceiver PHYs; they can transmit or receive, right?
Yeah, and then we can feed that from the system memory over PCIe. And then we've got the ISP front end.
We should talk about the ISP front end. Yes. I mean, I think we're going to do a whole session. We're going to do a whole video on ISP. But it's interesting that the ISP. This is the Raspberry Pi 5 is the first time we've shipped the new generation ISP. All previous Raspberry Pis have used the classic video call 4 image sensor pipeline. Yeah. But that comes in 2 components, doesn't it? There's a front end component which lives on Project Y and deals with the pixels, does some work on the pixels literally as they come from the camera, and then you have the larger ISP back end that lives on the main SoC.
And then on the display side, there's a DMA that again takes the video from the main memory. But
direct memory access.
Yes. So is the difference that there's more bandwidth on the CSI and DSI. Is that?
So I think where we've come from a world in which certainly if you're a Raspberry Pi, if you're just the Raspberry Pi flagship product, you have two-lane interfaces. You have a two-lane camera and a two-lane display. Compute module, the actual underlying silicon, or all the previous underlying silicon has had 4 MIPI interfaces. It had a 2-lane and a 4-lane camera and a 2-lane and a 4-lane display. What we have now is 2 4-lane transceivers. So strictly you have less on this platform. Strictly, you can only connect a total of 2 cameras and displays to the platform, but you can connect 2 4-lane cameras or 2 4-lane displays, and all of that functionality is brought out on the flagship product. It's not only available to you in the compute module world; it's available to you on the flagship. So that's MIPI worlds. This is additional additional bus masters in the system. What else is there? GPIO world. How does that work? So we have GPIOs, but you also have low-speed peripherals and muxing. How does that work? How is it similar to what we've had before, and how is it different?
So I think we have at least the same number of peripherals that we've had on previous platforms.
In particular on Pi 4, which was the one that grew all of the new peripherals. Yeah. And they're in the same, mux positions. Yes. So if I have become used to having a UART on a particular pair of GPIOs, I still have a UART on that pair, but they are different. They're potentially different peripherals, right? They're potentially different
types of
different
peripherals.
types of peripherals.
Yeah.
The UARTs, I think we established the UARTs are the same when we talked last. We established the UARTs are the same.
PLO11 ARM UARTs. And everything else is different, mostly from Synopsys, I2C, SPI. I2S is Synopsys as well, and then we have a transmitter and a receiver rather than a transceiver in Pi 4.
Yeah. SDIO as well.
SDIO, yeah.
So that's the kind of the bones of it. We have analog television out. We actually have VGA out, don't we, at the chip level?
At the chip level,
not on the board level.
Not on the board level. I mean, actually, the PHY, each channel so you've got 3-channel PHY on there, largely because sort of IP size-wise, it sort of made a little difference to have a single or a triple DAC, right? So it can do VGA. We didn't have the board area on Pi 5 to bring it out, and also the DAC's quite power hungry. So, there's constraints there, but at the chip level, yeah, you can do VGA with that.
You do VGA, you can do composite. You do S-video?
Is
there S-video with two lanes? Interesting question.
Yeah, have we ever tested it?
I'm not sure, but if we haven't tested it, then
probably doesn't work.
Moore's law applies. And then we can do wacky old style television as well, which is the key thing I'm looking forward to with Raspberry Pi 5, seeing the first person to get a 1950s telly, working with Pi 5. So you've got that. You've got DPI. I guess you can do the old style parallel video interface.
We mentioned Ethernet.
We didn't mention Ethernet. So what's integrated on RP1 and what's not on RP1?
So we've got the Ethernet MAC, but not the PHY. So the Ethernet's brought out to an RGM-II interface, which then connects to an onboard Ethernet PHY.
And this is a fairly similar architecture to Raspberry Pi 4, except that in that case the MAC was in the Broadcom device, but there was still an external, in fact exactly the same external PHY, 54213. Cool. So that's the overall structure. That's the overall structure of the design. How is it? We should probably actually. There's an interesting aspect, isn't there? That you talk about those streams of traffic that go to and from the design. There are 2 very different sorts of traffic, aren't there? There's real-time and non-real-time traffic, and how do they interact with each other, and what do we have to? So by real-time traffic, I mean camera and display data. If I don't get my pixel for the display in time, my display gets corrupted. If I am not able to unload a pixel from the camera before my FIFOs fill up inside the design, then I get a corrupted image. So those are real time. So there are, those things have to be done. And then you have things like USB. Now, of course, USB traffic can be real time as well. So if it say comes from a webcam, but most USB traffic isn't. Most USB traffic is best effort, particularly the high bandwidth USB traffic to UAS devices is best effort. So what are the challenges of making those work together? And when in the end the data travels together over a shared link, and what have we done? What have we had to do at the chip level, and then what have we had to do at the system level, and on the other side of that link to make that work?
Yeah. So the main bus fabric supports priority. So, for example, your camera would be highest priority because if your data doesn't get there, then you lose your image. And then something like USB can be much lower priority depending on the traffic, and that can get passed all the way through the fabric, all the way through the PCIe link, and all the way through to the other system, the main system on chip. So the main system on chip can get a version of that priority information to the point where I think PCIe can sort of reorder the way it does things. USB can have something queued up, but then if a higher priority message or request from a camera comes in, then that will get handled first.
So you're and then down at the main SoC, that can have a look at the data that's coming in, and it can say, oh, this is USB, because of course the same thing happens down on the main SoC, right? You've got HDMI data, which is real time, and so if it goes, oh well, I've got HDMI, I need some pixels to put out on HDMI, which is on the main SoC, and I've got a request from a USB drive, I can say, well, USB, you hold off while I go get my pixels that I need to scan out, my real time pixels that I need to scan out, or even conceivably hold off the USB for the ARM, because the ARM, while it's not real time, the ARM is not desperately latency tolerant. If you load a value from memory on the ARM, you're probably going to need it pretty quickly, otherwise your processor will stop making progress. That creates a problem though, right? There's a notion of head of queue blocking that we've had to deal with. What is that?
Who's going to answer that?
He was looking at you.
I'm looking at you.
Oh, God.
I mean, I'm going to give my management, if you're not careful, if you don't answer it, then I'm going to give my management level understanding of it, so you better answer it.
So,
What's the risk?
This is the risk basically that something is getting in, and effectively it's got the ability to pump a bunch of data because it's been given priority, but that data is effectively blocking the higher priority stuff coming in. Either your message, well, there's two ways, I guess. Either your priority message doesn't get through because it's blocked by somebody else's, or likewise the data, right? If you open the gate and you give it a bunch of window to give its data, and it either stalls or it doesn't shift the data in quick enough, then you can actually stall the thing that's high priority.
Yeah. So you have this risk, don't you, that RP1 has no real-time stuff to do, but it has a bunch of non-real-time stuff to do. And so all of the buffers, all the FIFOs in the system fill up with USB traffic. And then the camera wakes up and goes, I need to unload this. And there's a huge queue between your camera and the DRAM on the main SoC that's full of low priority data, and all of those components are looking there going, well, I've only got low priority stuff, I don't need anything to do, and there's this guy at the back of the queue waving his hand saying, hello, help, I'm running out of FIFO space. And of course, so the kind of the solution to this, the generic solution to this, and of course it's a thing that happens inside the main SoC as well, the generic solution to this is priority forwarding. So if I'm standing in a queue behind you and I'm high priority and you're low priority, I tap you on the shoulder and I say, you're high priority now. And then the next cycle you tap the next guy on the shoulder and say, you're high priority now. And sooner or later that priority, probably at one queue element per clock, that priority makes its way down through the system, and before you know it, the guy standing at the front of the queue, who's nominally low priority traffic because he's USB, is now high priority, and he's high priority because he needs to get out of the way of the real high priority guy who's serialized some way behind him in the queue. Now that obviously works well inside the system, and of course the fabric does priority forwarding. It's a bit more subtle, isn't it, when you go over PCI Express, because there isn't really a notion of priority forwarding, and we actually have custom vendor messages, don't we? Yes. So there's PCI Express has the concept, as well as a data payload message. It has a concept of a vendor message, a vendor signaling message, and we define a vendor signaling message which allows us to tell the main SoC, I've got panic. We call it panic. Very high priority panic. I have panic over here. You should panic now, and then that causes its end to panic, to elevate its priority. And then obviously it's another piece of co-design worked with Broadcom, so that PCI Express root complex inside 2712 is aware of these vendor messages and is able to turn on and off its panic state. And that's effectively the very long tapping the guy on the shoulder. It's the tapping the guy who's at the other end of the PCI Express in the queue at the other end of the PCI Express link on the shoulder and saying, yeah, panic now, please. So it's kind of cute. And again, the sort of thing that you need to discover. It's, you need to, I guess you've got to have the architectural awareness, the experience to know that this sort of class of issue is going to be a problem. And then you've got to have the time required to spec it properly, and then having spec'd it properly to check that it actually works.
And these things are complicated. There's lots of dynamics in these systems. So even when you've thought through a problem, you get it on the FPGA or the emulator and you spot something else, right? So again, it sort of speaks to the design, the time and the effort that's been taken in all of this stuff that, it required some iteration to get it right.
What did prototyping this platform look like?
So we used Pro FPGA systems, which allowed us to run, I don't know how fast it ran actually.
It's about 60 megahertz? Or am I just being optimistic?
No, I think you might be right actually.
So it's about a third. What's rated clock speed?
200.
200. So it's about a third of, which is good enough actually.
Yeah.
Right? So you have the digital elements of the design running at about a third the speed they would in the final chip.
Yeah. We had PCIe, USB 3, Ethernet, all the GPIOs. I don't think we could do every peripheral in a full system, but you'd have one USB 3 controller, for example. But you could decide to have two USB controllers and not put in DMA or something like that. But yeah, that's allowed us to sort of develop our Linux drivers alongside the system. And yeah, it's allowed us to sort of work out the areas, in particular, saying the priority, getting the priorities right and proving that works. You can sort of have a camera demo and then you give the camera the worst priority or the lowest priority, and then the camera stops working and then you fix it again. And so it lets you prove all of that stuff in the real world.
And we proved it against a number of different host devices as well, didn't we? So we proved it against 2711. So we've had a kind of a Raspberry Pi 4, but with Project Y world. We even had x86.
Yes.
x86. What did an x86 Raspberry Pi look like?
It looked good, except the software architecture is a bit different. So it actually becomes a little bit different to share the drivers because x86 doesn't support device tree, whereas the ARM platforms does support device tree, which is sort of how we tend to describe how our platform looks.
But you were able to build. We were able to connect Pro FPGA, so emulated RP1 in Pro FPGA to a desktop PC via a PCI Express card. Did we build PCI Express cards with silicon on in the end as well?
I think we did. Yeah.
So all of this work was done in FPGA. We had three major tape outs. We had an A0, B0, C0 tape out. Each of those, certainly the B0 and C0 tape outs, we then generated. Obviously, we had development boards, we had PCI Express cards, and that was kind of fun, right? That you actually really do have a PC, except it feels in its I/O world a lot like a Raspberry Pi, and it has Raspberry Pi. It's a PC, but with Raspberry Pi GPIO, a PC, but with Raspberry Pi USB, a Raspberry Pi USB or Raspberry Pi MIPI subsystem. It's kind of unusual to have a PC with MIPI, with MIPI interfaces on it.
It's the bring-up board is PCIe card shaped.
It's a big PCIe card with a socket, or you can solder the chip on as well.
And then finally, we had two generations of Raspberry Pi. There was I remember a Raspberry Pi 5 with the right-hand side cut off. So you had, for a little while, we had a 2712 board that stopped kind of
X4 PCI Express
an X4 PCI Express connector where everything on the right-hand side of the connectors and everything.
Pi 5 prototypes really started with that, with a massive, great proto FPGA. Sorry, not FPGA. Bring up board for Project Y RP1 in it, and then we iterated it again and put the chip down. Again,
and you did your usual. Explain to me that it wasn't going to fit.
Well, I do that until it fits. And
then I'm used to it. I'm used to it now. The first 3 or 4 times I found it alarming. One day it actually
fits.
fit.
Yeah. Wow, it does fit.
Yeah. I remember being shocked when Compute Module 3 was 1mm taller than the JEDEC. There's a JEDEC standard. Is DDR2? Is the DDR2 SODIMM?
TDR2 SO, yeah, the memory DIMM.
Yeah, and the CM1 is standards compliant and CM2 is 1mm taller, and I just remember the shock when a thing that you told me wouldn't fit actually didn't fit in.
No, sorry.
But it fit. It fit in the end anyway. So, and as we say, it does look beautiful, and it does.
Yeah.
Does
but I mean,
code design.
it is a thing. Like when you're doing board layout, you kind of don't know it's going to fit almost until right at the end. And I think, so I'm naturally sort of conservative and pessimistic. So I will always say it doesn't fit until it fits.
We had some substrate fun as well, didn't we? We iterated the substrate. It's quite a clever substrate. We iterated it a lot to get the cost down and performance.
The RP1 is designed to be a low-cost chip, right? So it's on 40, which we know and love. We haven't put any extraneous stuff in it. All the stuff in there is, we've sort of been designed for the platform as we do. The substrate is a 2-layer substrate. So
just in terms of the package.
Yeah, so the package, the BGA package.
By BGA, this is a grid of soldables on the bottom of.
Yeah, it's 12 by 12 millimeter with, I can't remember what the ball grid number is. But that's on 2. So substrates are like little tiny PCBs. They can have a number of layers, and you can then route the signals from the die all the way down to the pins or the balls. This is a 2-layer substrate, which makes it quite cheap. And we had to, and it's a wire bond chip. So the pads of the chip around the edges and wires, the little wires come out and bond down onto the top of the PCB substrate and then get routed to the balls. So we spent quite a lot of time designing the die so that you could bring those pins, those wires, basically straight out and down to a ball. Sort of makes the substrate easier and sort of, well, not easier, but cheaper. And we had to iterate that actually once because it's just a hard thing to do. So we had some sort of marginality in one of the power supplies based on the way it was done. So we had to rejig.
You had to go and fatten up the copper.
Yeah, we had to fatten it up and change the layout to reduce the inductance. But again, it's another thing that with effort we've managed to make work, and it's reduced the cost of that chip, even though most people would say, oh, you probably want a 4-layer substrate for that.
And it's a pretty cost. And it's a pretty cost. It ends up being a pretty cost-effective chip.
That's right.
It has all of the Raspberry Pi-ness in there, and it's not really materially more expensive than any of the previous I/O controllers. Our previous I/O controllers have done 1 or 2 things. Have done USB hubbing, or they've done USB hubbing and Ethernet. This has all of the Raspberry Pi-ness, and really, in terms of the cost impact on the design, it's about the same.
That 2-layer substrate makes the ball out sort of a little bit weird, but it's fine because we could iterate it on the Pi and just say, okay, it works now. It looks a bit odd. Looks slightly less neat than you might get from a sort of one that's been designed first and then designed the other way around. But it works fine.
Yeah, it's a lovely platform, right?
It's a lower cost.
As I say, it's gone through three major iterations. It's gone through, over a long time, and of course, it's the reason why we have a chip team. And also, I guess we should talk a little bit about tooling. It sort of justified the creation of some of the tooling that then made the RP2 device, RP2040, easier to build.
Yeah, so RP1 is sort of built from the same scripting architecture that was used to make RP2040. Generally, anything that we're going to repeat, whether that's repeat across multiple chips or just repeat on the same chip, we tend to sort of script up so that you can build it from a specification. So all of our clock generators are built up from a list of, you specify a list of clocks that you need, what size the dividers should be, what features they have, and then that will just stamp out 10, well, it's 5 on RP2040, and then on Project Y or RP1, I think it's 20 or 30, or there's lots of clocks on there.
30 actually.
Yeah,
It's really taught me how much of the complexity, the power and clocks complexity of the classic architecture is actually in the analog elements rather than in the fast digital elements of the design. Right?
Yeah. And the reason we've got so many clocks is tends to be audio and video are quite fussy about the clocks that they need. I2S is as well. And then, so we do that with clocks, we do that with resets, we do that with sort of power on state machine, which takes things out of reset in a particular sequence and waits for each thing to be done. We do it with the GPIO muxing. So the GPIO.
Is that done that way on projects on RP1 as well as RP2?
So it comes from a spreadsheet. So basically, the spreadsheet that's in the datasheet is the spec that goes into the tool, and then it does the right thing. There's some other bits as well. All the general wiring. So you say, I want my chip to have 2 USB controllers, 2 SDIOs, etc., and then it will go and instantiate all of that for you. It wires up the bus fabric, spits out the address map.
Spits out some of the headers and stuff for software.
All the documentation, software headers.
It's cute, and I mean, I guess we've all had some experience in ASIC development before this, and it does feel like an extra level of performance beyond the two. All organisations have some level of design automation at that point, but somehow we seem to have managed to take it to a higher level than we've seen before. Which is kind of fun, right? And it helps us have a small team. It helps us have a small, efficient. Of course, small teams are challenging, right? Because there's a lot of work to do, and you only have a small number of people to do it. But small teams are good because you can have enormously high caliber. It's easier to recruit a small, high individual caliber team than it is a large high individual caliber team. And also the amount of time you spend talking to each other when you're a small team is more than linearly better than a large team. And a lot of this work you did with Terry, right?
Yeah. So I was, I guess Terry's understudy. But Terry is the guy who's written most of these he would describe them as highly parameterizable components. And that's a clock generator, the I/O muxing, the pad wrappers, the reset slice, we would call it, the power slice. We call all these things like clock slices, etc. But the idea is you sort of stack them together to make the block that you want. It also means that we can sort of verify that as a standalone item and then call that known good and then stamp them out as we need.
And it's this idea, I think, that we've come to of having a team which is not quite starving. That you have a team which is where you have slightly more than the minimum amount of resource you need. So you have little enough resource that there's a strong incentive to look for design automation opportunities, but a large enough team that there is somebody available to do the design automation, right? If you're situations where teams are starving don't generate innovation. Situations where teams are under some resource constraint generate innovation. And it's really cute.
I think we've got enough seasoned hands who are been fed up of typing lots of stuff that we've typed in 10 times already, that having this tool has just made everyone's life so much easier.
And it made RP 2040. I mean, RP 2040. We should probably talk about how RP 2040 fits into this flow, right? RP 2040 was kind of multiplexed onto the same design team, really, as a way of at the time it felt like sweating some extra value out of our investment in ASIC engineering. It was feasible, I think, because a lot of this design automation, and in there you have AHB fabric that's automatically assembled as well. So you have this level of automation. From my point of view, I think it's done another helpful thing, which is it's meant that RP1 is not our first production chip. RP 2040 was an interesting chip to get into production because, of course, it went into production during a pandemic. It went into production during a supply chain crisis, but it taught us a lot about operations. Obviously, John Matthews joined us to run the operations element of the organisation. I think it would be quite scary, right, if a chip which was in our flagship big Raspberry Pi product was also the first piece of silicon that we did.
Yeah, I mean, the production test for RP 2040 is relatively simple compared to RP1 because there's so much analog on RP1. The tester has to be more complicated and there's lots more to test.
But interestingly, we're using the same tester, aren't we? We're still using J750 for it. We use Teradyne J750, but with a sophisticated load board. I think that's another thing that we learned, another thing that we really learned. Well, I think probably a thing John knew or suspected, another thing that we learned over the course of RP 2040 was that you can get away with a very cost-effective tester, and then the load board that adapts the chip onto the tester. You can put some of the analog components in there.
Yeah. So I think we are using J750EX, which is the slightly slightly shinier one, but it's still a low-cost tester. Which is great.
So I forget what it was we were planning to use, but it was hellish, wasn't it? It was a very, very complicated tester before.
I can't
Yeah,
remember.
what are they called? Those Ultraflex.
Ultraflex.
We're going to use Ultraflex, but we've been able to use J750.
And how many boards can we test in one go?
It's a quad site, this one.
It's quad site.
So for
RP24
2040
is
is
octal
8.
site. It's octal site,
And then
right.
we do 4 for this one.
Yeah. Which is still very wide. Very few of the chips that I've worked on in a previous life had even quad site testers. But it's fun. It's fun. And good to have another chip. Good to have another chip in the wild. Good to explain to people what the ASIC team has been doing. You know, it's good. Excellent. Well, anyway, that's RP1. It probably accounts for, of that $25 million. It's substantially more than half the cost of developing Raspberry Pi 5. But it's been fun to do, and I suspect it will probably be with us for a little while.